This lecture is an extension of the previous one. We talked about end behavior to determine if a graph was going to have an even degree or odd. So this would have an even degree because both ends go in the same direction as your x goes toward a positive and negative infinity. This is going to be an odd graph because your end behavior for your y's are in opposite directions as you go in toward negative and positive infinity. So this would have an odd degree. This one's going to have an even degree, and this one's going to have an odd degree. Okay, and to determine what the degree was, remember we looked at the number of turning points, and the number of turning points has to be is n minus 1. So whatever the degree of the polynomial is, the turning points are 1 less than that. Since this has 3 turning points and this is an even graph, this one right here, we had to at least have degree 4. All right, and then you checked your intercepts to see how many intercepts you had. And here we have 3. And remember, the fundamental theorem of algebra says the number of roots you have cannot be larger than the degree, or the degree has to be the maximum number of intercepts. So we have 3 intercepts. This is a 4th degree, so we're good. This one, we had 1, 2 turning points. And so we knew that this is an odd graph, so it has to be at least x to the 3. And then you checked your intercepts to make sure that, sure enough, we have 3. We can't have 4, or it would have to be a 5th degree. So you can't have more x-intercepts or zeros than you have power. So that's how we came up with these. And then we decided if they were negative or positive. This one is going to be negative because even graphs that go down, you can think of this as kind of a crooked smile, are going to end up being negative. And then for the odd degrees, you went ahead and you found your rate of change from the starting point to the beginning. And if your slope ended up going down, then it was going to be negative. So that would also be negative. Okay, so that was just a recap real quick of what we talked about before. What we're going to talk about now is multiplicity. And multiplicity is once you've figured out what your degree is, then you need to write your particular function in factored form. So this is going to be a negative x to the 4, and this was a negative x cubed. So the question is, we'll just call this polynomial. We'll call this one p of x. P of x is going to be equal to a factored form, and you go backwards by finding your zeros. Okay. So we want to write this in factored form. So let's do the 4th degree first. So we know this has got all real roots because it touches the graph and there's none. This up down here at number 9, this is what it looks like when you have an imaginary root, which I'll get to in a minute. But if you have a turning point where the graph turns and doesn't cross the x-axis, then you have an imaginary root, and you cannot write something like that fully factored off the graph because you can't see the imaginary root. So I'll talk about what to do in that in a case. Right now we're just going to stick with ones that all the turning points create roots that cross the x-axis. So again, we have a point here, we have a point here, and we have an x-intercept there. Looking at that first one, this is minus 2, 4. These are counting by 6s. This is going to be a minus 6 at this point. This is going to be a minus 1 because, again, each of these ticks is 2, and this is going to be a positive 6. So if x minus 6 is a root, then x plus 6 is a factor. If x minus 1 is a root, then x plus 1 is a factor. And if x equals 6, then x minus 6 is a factor. So each of the roots become factors when you plug them back in. And again, you just change the sign as you do this. So x minus 1 was a root, and this one created positive 6 created a negative root. So that's where you go from roots to factors. Now, we have a 4th degree polynomial, and right now we only have 3 factors. And there are no imaginary factors, so we need to figure out where that extra factor is coming from. And that's where multiplicity comes into play. If the graph crosses at the x-intercept, keep turning this into a C, okay? The multiplicity is odd. Now, most of the time, it's going to be a multiplicity of 1, but we'll see a couple cases where the multiplicity is actually going to be 3. Okay, and it could be 5 as well. If the graph just touches and does not cross, if graph touches, at the x-intercept, I'm going to go ahead and abbreviate so I have enough room, then the multiplicity is going to be even. So you're going to have a square, a 2 root, a root that occurs 4 times, etc. Okay? All right. So, and you figure out what this is, which multiplicity is based on whether it crosses, and then you figure out whether it's a 1, 3, or 5, depending on how many roots you need to get to your highest power. Okay? So let's look at this one. This was an x to the 4th, and it's negative. So in factored form, got my roots. There's going to be a negative, and there might be a coefficient, or it might not. So the a might be a 1, but you're going to have a negative something multiplied throughout this polynomial to make it negative. Now, if a is a 1, it just puts a negative in front. If a is like 2, but I'm not going to worry about that right now. We're just going to go ahead and look at the multiplicity. Okay, so I have 3 roots. This is a 4th degree equation. So the question is, do I have a multiplicity of one of them? Well, the root at a -6 crossed, so that would have 1 or 3. Well, we can't go up to 3 because then it gets bigger than our degree. This is a 4th degree, so I can't have more than 4 roots, 4 factors. This is touching, and I need to get up to 4, and right now I have 3, so that means this is going to be a squared term. So what we have is what's called a double root, where the x plus 1 creates the extra 2 factors. So now I have 1, 2, 3, 4 factors. Okay? So that gives me my 4th degree power. So the multiplicity, you kind of have to just use a little bit of common sense. If it's a 4th degree, how many do I need to make it the same as my exponent or my degree of my polynomial? Again, this is a little different when you have complex roots, which we'll talk about in a minute. But if all the roots are real, then something has to be has a multiplicity to make the total number of factors equal the degree. So the degree here is 4, and hence I need to have 4 factors. So somewhere in here there is going to be a multiplicity situation, and that was with the plus 1, or the root of a -1 touched and didn't go through, so that's going to be square. Okay, so this ends up being square, and I'm done. This graph was a cubic, and it was also a negative. So let's look at the roots here. We have 1, 2, 3 roots, and it's a cube, and all of these cross. They don't bounce, and we need a cubic, so that means each of these is going to occur just one time. So what we see is what we get. So we start again. P of x is I'm going to call the polynomial P of x. I have a negative, so I'm going to start it with that negative coefficient. It could be a 1. And then it crosses at a -2. This is a -2. This is 0. And this is 2. Okay? So the -2 becomes x plus 2. 0 just becomes x. And 2 becomes x minus 2. And there's nothing else for me to do because there are my 3 factors. This is a cubic, and I needed 3 factors because they're all the roots are real, so there's my 3 factors. And of course, if this was like a square root of 2 kind of a root, you would have to estimate. So most of these go through points that we can see. First, figure out what the degree is. We have 1, 2, 3, 4 turning points. So this is going in opposite directions, so it's got to be odd. So it has to be at least an x to the 5th, and then I'm going to check my roots to make sure that works. I have 1, 2, 3, 4, 5 roots, yes, and they all cross. So once I find my roots, I turn them into factors. I'm done because this is an x to the 5th. Is the minimum. Now, it could be bigger, but I'm just working on what has to be the minimum to make everything match. So this is a -3. The first root is, that looks like that crosses as a -1. We have a 0, we have a 1, and we have a 2. Okay, so my polynomial, and then I also need to know the sign. Going from here to the other one, I have to go uphill to get from one end of the graph to the other, which means it's positive. So whatever my coefficient is, it's going to be positive. The -3 becomes an x plus 3. The -1 becomes an x plus 1. x equals 0 would be x minus 0, which is just x. This becomes x minus 1, and this becomes x minus 2, and there you have your factored form. There's no multiplicities beside 1 because all of these cross, they don't touch, and therefore they're going to be odd. And since I needed a fifth degree and I've got 5 roots, I'm done. I don't need to do anything else. I'm trying to clean all the little marks off for those of you that leaving marks on drives crazy. Okay, here's another one. This is a even. This is going to be an even graph because the end behavior is going in exactly the same direction. We have 1, 2, 3 turning points. So for an even graph to have 3 turning points, it has to at least be a 4th degree. Count our intercepts to make sure we don't need to go up to 6. We have 1, 2, 3, 4. 4 intercepts, so they're all crossing. So these are all going to have a multiplicity of odd multiplicity, which in this case they're going to be 1. So let's go ahead and write this as a polynomial, p of x. And again, this is now a positive. So it's just going to be a, and we have x plus 4, because this first root is through a minus 4. This is through a minus 2, so that becomes x plus 2. This is through a positive 2, so x minus 2, and then I'm going to write this last one down here. That goes through a positive 3, so that becomes an x minus 3. And there's my 4 roots. I needed 4 roots, and they all have a multiplicity of 1 because once I write out 4 factors, I am finished. Next, I'm going to find one that's some that are a little more interesting. Let's go ahead and look at this one, number 9. That has end behavior that goes in opposite directions. It's positive, so this is going to be a cubic. I have 1, 2 turning points, so that fits that I need to have at least more than 2 turning points, and I only have 1 root. What happens here is your polynomial is positive. It has, this looks like a negative 3 as a root. It has x plus 3 as a multiplicity. But you've got this imaginary, what happens up here in this area is you've got, whenever you have a turning point that's not touching the graph, you're going to be dealing with imaginary numbers. So there is, if you remember back when you do the quadratic function, let me go ahead and just make some numbers up here. Let's say your imaginary answer, let's say you got 2 plus or minus I square root of 2, okay? What you have is you have 2 plus I square root of 2, and you have 2 minus I square root of 2, okay? Those are your 2 missing roots. That, and if I knew that was them, I would put them in here. I don't know if these 2 are in there, but that's where one imaginary, and there you get your 3 factors. And you get your 3 roots. Obviously, you can't write that in factored form because you have no idea what those imaginary... Actually, there's a way to find it, but this is beyond the scope of this class. So you're not going to be... You might be asked what's the multiplicity of the root 3, which you would say is 1, and what's the degree? It would still be third power. It's just you could not write this in factored form because you don't know what the missing roots are. You don't know what these imaginary roots up here are. Obviously, it changed directions, and it had a turning point, but we can't find those. So all that you would be expected to know is this is a 3rd degree, minimum of 3rd degree, and it has, 2 turning points, and that's how you know, but you wouldn't be able to write it as factored. So that's the kind of thing that you would not be asked to factor because you have no way to do it unless you're asked to solve it. Now, if you're asked to solve something that gave you 2 imaginary roots and one real root because it was a cubic, then you would know that it would look something like that.